7:30 p.m. ESP32 cams, dude. I don't know how good they are, but yeah, no, for face tracking and stuff, right? It's pretty good. Diddle-a-do. So what are we doing here? We are looking at my reaction chart, and again, I've got to work this out because like, what's really annoying for me is the idea of how I want to have gas logic work for elements in terms of how refinery can work, and yeah, you'll get some really weird effects. Okay, let me check this format. I'll change it there. Yeah, there we go. It's too big, it's too small. See, what I wanted to do is have so element logic for this specifically, like there are a couple of factors that I wanted to have, like stasis, which is when time stops, inversion where time reverses, dilation where time accelerates. In terms of something that slows down as well, so the reversing of entropy is inversion, but that's basically from 100% down. But basically between 100% and or 1%, I haven't got that, so I need to figure out that one. That's 0% is stasis, so there is another one. So let me just copy this down here. There you go. No, let me just again. There we go. All right. So stasis and we can say entropic dilation. No. Okay, so contraction, we'll use that word. Again, I kind of want to get this down as a something that I can actually use brain-wise. Okay. So what is entropic construction, basically dilation and stuff? So let me just change this. Reduces. %. Okay, that's fine. Reduces the flow of entropy, increases the flow of entropy. Okay. All right, so what this is basically the speeding up or slowing down of time, but it's not the reversing of time. The reversing time is inversion. So basically temporal inversion. So these are sort of like your sci-fi effects that you'd have because of faster than light travel. But these four effects must actually exist, or actually there should be five effects. I'm gonna have to move stasis up here because again, and then what we'll do is we'll actually change it to the to an entropic family. Okay. No, I need to remove you. You need to be here. So decay is this, and this is again, this is decay. So that's basically what happens after the effect of entropy. So basically where something ceases to exist. Temporal inversion. Okay, that's bond. And then absorption, fusion, bonds. So again, you'll have basically time-based effects and physics-based effects. So they're all part of physics in the family. You'll have absorption, something that bonds. So basically something that it becomes the same part of it. It's the elements are separate, but they're bonded. So a simple example of a bonded material is like a composite, like brass, for instance. Brass is tin and copper, right? And we all know that. We played Minecraft and we played World of Warcraft and all the other crafts. We know about that specific stuff. So yeah, steel would obviously be tempered iron. So yeah, you'll have carbonized steel. So again, it's the treating, it's the way that you treat the iron to create the steel. And the types of like you got magnesium and other types of materials that will go into this. So if we're going to do like an actual full physics layer in terms of sort of like treatment, with regards to sort of like there has to be a sort of like what is it, time frame. So I need to do like a for regards to if we're going to do any sort of because I might make a PDF of this. See what they say about it. Oh, okay. So I was also looking at evaporation. So different types of ether extraction. So mixing. What would be cool? Like what would you say is mixing? The mixing process in engineering. So again, is there a scientific term for mixing? A mixture is just physical. So anything like distillation, separating, and stuff like that. Because we have to, again, when you do the molecule, the actual material value needs to be able to have its own sort of like effect, right? So how it affects and what group and family it's in. So again, you'll have the gas, solid, liquid formulas, and it's basic logic. You have to start from a basic thing, and I think we could do like a 5-point star and have like ribs across it, and sort of like see if you can get sort of like a formula of doing like a pie chart or whatever. I know it's bad. See, do you know the most irritating part about touching grass is every time I go out and touch grass, I get new ideas and I don't have anywhere to kind of like write them down at the moment. Check this stuff. I want to see if I can get my chat up. Okay, there you go. All right, I have chat. Awesome. Just in case anyone drops in and starts spamming my shirt. See, this part was actually kind of fun to do, but then once you've actually got to this point here, the effect on time. So again, radiation, how pressure affects elements. Pressure has to be applied using either a liquid or a gas or a solid to basically pressure would be the passing. So it's again, you'll have one material will only go up to a certain point to where the pressure point is, and then it's a case of it will either be absorbed into or it will be, absorbing whatever's being pushed into it. So it's like you know, if you and steel, right, basically a hydraulic press comes down on you, right, which one's going to win? Yeah, this is why hydraulic pressure is kind of like something that we can use as well for refinery. Actually, in process, you could use what's going on here? Why is this like this? This doesn't make sense. It does make sense. Oh, okay, it makes sense because I had it paused. Anyway, okay, that's cool. So anything that's creating pressure, you'll actually create an energy element to it. So applying to pressure, if two particles are actually pushed together using an inert gas, so if you create a volume, right, of two materials, and then you use a gas or a liquid to combine the two. So again, the mixing process is suspension, so stasis. The controlling of substance using pressure or stasis, right? So you can use stasis. Now, stasis is a suspension element. So anything that is that slows down a flow of atoms is considered a stasis material. You'll have ones that are entropic dilation and entropic contraction. These are quantum effects. Decay is a post-quantum effect, and temporal inversion is a quantum abnormality. I guess it's a quantum effect still. So I'm gonna have to work out. So we'll try this quantum effects. And then we'll just put that on the actual board, and then we can actually add those to the entropic delay, stasis world. So you'll have different chemical bonding agents, pressure. So there are always going to be different methods of how to combine two materials together. But again, it's a lot of the things, like for instance, heat is mainly going to be used in materials that are like stone or metal. So most ferrite or non-ferrite metals, etc. You can melt them. So if it can be melted, you use energy, you create radiation. Radiation will affect the material. So again, it's sort of like those sort of bonds. And then entropy is a relation to anything that flows forward or backwards in time. In terms of accelerated, so if you accelerate the entropy, so if you do entropic dilation or entropic contraction, depending on what you're using to create the field, because obviously science, we get temporal fields based by quantum anomalies, which can be used with technology like quantum drives anyway. So the shield technology I want to actually talk about it's going to use the effect. Okay, so I have to work on the input. So the input of fusion is energy plus 2 bond material. So basically, fusion is this temporal inversion, stasis. So this is all right. So contraction. So this is slowing and this is speeding up. So anything that goes this way. So this is the flow of time from stasis. So 0 seconds. So this is still, this is non-movement. This is motion, and this is reverse motion. Yeah, and we can go backwards to. We have to look for the. All right, so negative. I think that to negative entropy. So all right, so that is. So 100 to minus. Douche. So to minus to minus half-life. So basically your full life. wait, no, this is entropy inversed. Okay, so this is basically a complete inversion. Total inversion. Okay, that makes sense. So entropy is reversed. Can we go one layer up? So a temporal inversion, and then a temporal. What would it be if you kind of like you were Spock and you basically was reborn again? So resurrection. No, I can't use that one. We'll just call this inversion. Because we're going to go with the Christopher Nolan version of it, which is when it's basically time scale is reversed completely to 100%. So that's inversion. And then reverse entropy reversal, which is anything that goes from negative 100 to and we'll call that infinite. Actually, we'll go with the where's the infinite label? We'll have to find one. There we go. It's minus, so it's to minus infinity. Okay. So I'm just, again, we're doing theoretical behaviors here. So I'm just looking at sort of like how I can apply sort of like a physics bubble and how a shield will work, etc. So once I have the sort of like the elements down, absorption, the effect, insert, no effect. Fusion. Two elements are forced in. Quantum effects. Okay, chemical reactions. Let's try that one. Let's add that. That's a bond. So energy. Energy reaction. Fusion. Chemical reaction. Absorption. Delete that. No. You should see what I've been working on. Laws. Anyway, previously on X-Men. Okay. Do you know what's really the most irritating thing about being big brain and like knowing how to do things like this specifically, or at least being able to work it in your head how these things could be done? It's like once you work it out and you've actually got a thing that actually means something, like a body of work, how you utilize it is like pretty crap, because it's like depends on where you are in the world, man. Like, dude, you know, the dude who invented Tetris would never have had his big break had his game not been like, you know, someone trying to sell it in another country. Because again, yeah, maybe that's what's gonna happen with me. Communist, they just use me to like. I'm just gonna basically create the logic for the simulations. Yeah, the funny thing is like once you get to a point where you can like work things out, explain them, and that. It's like I'm pretty sure it would make it a lot easier to code, because it's like, oh, so okay, so I need to make this do this effect. Yeah, that's what you need to do, bro. Stasis. I'm gonna remove this tag. Actually, screw that. Don't need it. So elemental effects, fusion energy. Why is this? So element energy, release plus energy or negative energy. So basically, I'm going to have to put a plus or a minus, because we're going to do absorption is negative, negate in energy, so it absorbs out. So that's an absorption, and this is a production, because fusion is pressure plus elements. So pressure plus element A and B in terms of how you do it. So fusion reaction, fusion, pressure. Okay. So in terms of energy, is it if it's it right? Okay. So fusion. What is? I'm gonna have to find it when you bond. The Van der Waals force. So therefore, anything that holds noble gases together is called a Van der Waals force. Okay, dude. Like this is the crazy part. Is like if I start working out how to explain things in my own logic, and then I start understanding quantum math, and yeah, that's when we get a bit. Hey, dude, you're actually talented, and we could have used you this whole time, but well, we basically treated you shit in school and made it so that you felt like an oddball and you couldn't succeed in life because you're too intelligent. Okay, so noble gases: helium, neon, argon, krypton, xenon. Yeah. Um, what was like this is the thing because everyone's like getting all like wet and moist over Dune, right? Dune came out, everyone went to see it. I think it's the best film since Last Bread. I'm like, you're cringe, go away. But they did get a few things right, which is the visual representation of the Thopters, the visual representation of the building architecture. I like that, and definitely the shields. I think the shields they got correct. Um, but at the same time, that's when I started actually thinking, well, how do these shields work? So again, the smell, Freon, yeah, it's that sort of like that smell that you get. What kind of gas is Freon? It smells like chloroform. The Swedish car coolant. Oh, I know what Freon smells like. It's a horrible. But yeah, some of the novelists back in the 70s, they were all over the place with the Freon smell. And like yeah, it's laser. Anyway, so what I wanted to do again, the idea is just having different methods that you could actually explain, right, to show an effect, and I'd have like the effects would be silly. It'd be like you'd have like this. There'd be an element here, an element here, and an element here, and then there'll be circular sizes. Okay, so this is element one, element two. So in terms of that, element A, which is gas, element B, which is a so, mineral, element C is, say, a corrosive enzyme. Okay, corrosive enzyme. So enzyme breaks down this one, this one. So basically what will happen is the corrosive enzyme is used as the absorption. So what we'll do is we'll combine relationship with this relationship is this with this, and then we'll also do another relationship with this and this. So this here and this is the bond. This here and this is so this is a stasis element, and the relationship from this to this is a decay element. So because that's it, And then the element here to here is the bond. So again, yeah, we're just going to move that to this side. And so that's stasis and decay. So this element is decayed until it becomes weak, so the gas can actually impregnate the mineral, or the mineral is absorbed, so it's dissolved and then mixed in the corrosive enzyme with the stasis, which is where the gas is. So basically, you carbonate it in terms of how you would make it. So I mean, I'm working on the improvements of sort of like, once I get the descriptions down, like it should become a lot easier to sort of craft something that's feasible. There you go. Doesn't that look nice? Okay, so what is this topic? I don't know. If I do things like this, it makes me look intelligent, which is all good. Okay, so again, we do the same thing. We're going to change the color of this. So this is a gas. So let's make it a bluey stuff, and then we'll make this one. This is a mineral. So we're going to make it make it orange or red. Actually, red's usually the color we can use. So red, because it's a mineral. Corrosive enzyme. Yeah, we're going to go with green. We'll go with a puke green, actually. Or lime green. So something like that. Okay. So, and then we'll work on the colors for the specific color coding of each of these things. So the bond between the two here is chemical bond. The chemical bond. And that's basically, you'll get, for the chemical bond, for it to break, it actually has to have a threshold. So we can just maybe put it here. Okay. So what is the bond? Chemical bond. Okay, so let me just, if I do this, I add this to this, and then this to this, a chemical bond. And then we change this one to dush. So it's a chemical bond. So this is free. Corrosive enzyme. Stasis to this. It decays this, dissolves this. Okay, so let me just put that in relationship dissolve. Okay. All right. So I'm looking here at what behavior I want to do, which is I'll have decay on the molecular bond as well. Again, this is, see, I'm not trying to kind of like make things up without logic. That's why it's good to have these sort of exercises. It's like a Sudoku puzzle, really. Because you're trying to work out how an element will behave and then have a sort of like a mathematic formula for it, and then you apply that to a problem and it should make everything easier. So the molecular bond, we can use white as the color because white is the right color for a molecular bond. Why is it not? Why is the fill not coming up? Oh. There you go. Molecular bond. Okay. And the molecular bond is actually the smallest part of it. So again, we're just going to increase the size of these just a little bit. And then a little bit there. So volume of control. So again, this is the percentage of the enzyme. So if you want to completely, you do it to a container, again, you'll add this particular here is, those are boundaries. So that's an actual element. Composite element. Wait, did I do the same thing over here, right? So this is a base element. So this is research container. Da, 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 da. Yeah. Okay, so base element is a bond and an additive. So again, we're going to use the blue for that bond and additive. The bond, okay. And it should be like this, actually, shouldn't it? No, wait. And then it's how much of that is void? Okay, so percentage of experimental container that is vacuum. Okay. Okay. structural integrity. This is stable within the structural. So a bond between two elements. I gotta pee. A bond between two elements with stable thresholds, blah 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 blah. Integrity. Okay. Note. Base element. Additive element. plasma, gas, liquid, solid. Okay. Etc. I don't know if I can actually add a whiteboard thing to it. Phases of matter, so between solid and liquid. Yeah, I'm just going to Google something that I can use. Ionization, deionization. So so ionization, evaporation, melting, freezing. All right, we got the 5 states of inversion and reversion. So again, from plasma is ionization and deionization. Okay, so but I'm also working like, again, everything can be consumed by plasma. So solid, gas, liquid are absorbed into plasma. Liquid, solid, absorbed into gas, so it goes inside. So a solid can go in liquid, but it can go inside gas and can go in plasma. So we're looking at this Russian doll sort of like effect as well, where a solid can go into a liquid, but a liquid can't go into a solid, right? A gas can't go into a liquid, and a plasma can't go into a gas, but a gas can go into a plasma, right? So again, it's a plasma can exist in void. So we're going to do vacuum as your final element. So void is just basically empty space. It's nothing, zero. Ionization to plasma gas, evaporation, condensation, vaporization, condensation, I need to make sure I get it right though. So it's which one's that? It's ionization is yeah, okay. So ionization, I'm going to change this around as well. So we'll do void plus okay, so we'll do what is solid, liquid, gas, plasma, ionization, deionization, equilibrium. Ionization, which is again forward entropy into plasma. So again, okay. So ionization is this. So creation of plasma becomes deionization, creation of plasma, creation of functions, plasma gluing into glass, vaporization. And then there's other forms of okay, so again, pressure is another way of condensation. Condensation. Okay, so condensation, melting and freezing. So melting. Again, some like you can't melt all solids. Again, like fibers, for instance, because fibers would melt at sort of like anything that's fiber based will actually burn and sustains because it's like burning a candle, right? So the idea of a fiber is essentially the same thing as a candle, is that basically the surface area will be uh, melted. So a reaction is actually downward. So the energy reaction is from the top to the bottom. So it falls to ground, and then you have the separation, which is in equilibrium. So it's kind of like a distillation process. So again, distillation is an absorption, or sort of like they're the processes we can talk about after this. Freezing, slowing. So again, slowing down or slowing down of atoms. So again, everything is the speeding up or the slowing down of atoms in entropy. Again. Okay, I think I'll think. What's the opposite of vacuum? Like positive pressure. Okay, so I'm trying to figure this one out. This is right. What I want to describe is a process where you the additive. Okay, so element, so additive and bond. Pressure and radiation, free pressure, radiation, and entropy. So time. But we'll call it entropy because again, it's a third state of space. Okay, so a virtual composite technology. Okay, so why do I use the term quantum? So basically, a quantum field can create an entropic effect. Okay, gases and liquids can also create entropic effects on a natural scale. So basically, this is like when you're swimming, right? So what happens is you're falling through a material that's viscous. So it has sort of like you have buoyancy in the equilibrium because you are also containing part of that element. So he who contains that, he swims in, can dominate and basically can move freely around. And that's essentially what happens with water. It's the case that you've got the buoyancy, equilibrium, and you're able to swim. And if you obviously want to sink, you've got to remove buoyancy. So you've got to remove air or increase weight. So again, so those are sort of like factors that I want to sort of like take into account. And like this, the thing that is that I'm talking about is all just because I want to do a shield. Okay. And all the shield is going to be is I don't know if I can add a whiteboard area or something. Insert floating topic. Insert relationship. Insert subbranch. So all right. So what I want to do is let me create a shape here. This is kind of like. All right. So. So here we go. It's a shield face. All right. And this way we've got, okay, so we've got shield face, shield face, shield face, shield face, right? And then we can actually emitter. All right. So a shield face will project basically you can project one shield face, which is a large shield face, which is a 4-point shield, or you can have what we call as the fun part is the emitter. So it's the emitter predicts how many shield faces you're going to have. So are they going to be in parallel like this? Okay. And then what you'll have is you'll also have not shield face. Okay. So again, copy that, paste that. All right. So this shield face, and then we'll have a quantum field. So we'll have a dissolving gas, which is a corrosive. And then we can also have an interference, so it's a suspension field. So shield face, quantum field, and dissolvent gas. And then So shield core. All right, we're going to change the shape of this. We're going to make this oval shaped. All right, so we've got shield face and dissolvent gas, shield face and dissolvent gas. So what we're going to do is we're going to add that to that, add that to that. So these are your layers, and this is the shield emitters. So this is the shield core. This is the inside. So we have the shield face, and then we'll have the outer shell, which is what's going to, you know, all of these will be connected to. So I'm going to do one better, and what we'll do is we'll actually do the quantum field. We'll put the dissolvent gas, and we'll just put the hardened shield. And not only that, we'll also include a relationship to the quantum field, which is, again, we don't really want to. Relationship is okay. What if I remove that, and instead of that we just insert the dissolving gas as a shield anomaly, and this is the shield itself. All right. So shield face dissolving gas. So we'll just do that. We'll put the shield face inside of the quantum field. How do I, like, I've got to figure out a way to put that inside it, like if there's a way to do it. Insert yikes. Okay. So in terms of, okay, so this is a sort of like a triangular faced emitter, right? So the shape of it will be pretty much triangular. So see if we can create a triangle here. It's a shame there's like no way to do it properly. No, because you can't like do a basically never mind. Doodly-doo. So the shield core, which is this part here, and then this shield face. So we'll do this. So, all right. Shield face, shield core, the jam filling. Oh wait, no, that's the jam filling. Okay, so this is the stasis element and the, okay, corrosive element. Let's make this about 24, there you go. Just a bit bigger. Stasis element, corrosive element, shield face. All right, I don't know. I'll call it a shield face. We're going to change these to, I don't know, 18. So, yeah, okay. And then that way we actually got this. So the reason why we do this in phase, so this is a shield emitter. A single shield emitter will hold phase for free. So this is basically a tri emitter. The angle. Uh, okay. Another thing that we could do is like again, if we make like again, if we create an elemental based weapon, yeah, that uses the physics from this sort of plan. All right, you can create chemical rockets. Like for instance, say you've got a dissolvent gas, and you can actually add a neutralizing agent to your missiles, which can, depending on the gas type. So if you know what kind of like the common gas type being used for shields in the area is, and you develop, so using science gameplay and a lot of hours of experimentation on that particular gas type to find out what breaks its bonds down, right? What can dissolve it and be lightweight or not, you can pack it into a missile without creating anything that can survive an energy blast, for instance. So if we create a chemical based missile, what is the impact field going to happen? Like, so what is that specific missile is going to do? Is it's going to enter the actual quantum field as it passes through the shield phase. So it pass through the shield phase into the dissolvent gas. Now, the dissolvent gas will eat away at the shield because it's in the stasis field. So this is the stasis element. So the stasis element reduces the time scale of no, I've got to figure out a way to actually explain this in a little bit less of a stupid way. Reduces the time scale of an object within it. Right, let's not talk about it like in terms of that. Atmosphere you pass through. So in terms of the all right, so it reduces the reduces affects the timescale. Okay, let's not say reduces, affects timescale of an object within it. Electromagnetic. Shield core. Um, light energy fields. Okay, I want to do the same here. Shield face and shield core. Okay, no. Thing. Okay, so stasis element. Okay. Okay, so manipulation of shields and the array. Okay, so the array shields will manipulate in terms of like, so I think I'm making rules that are, I think, okay. But I want to talk about just the shield, right? So we're not going to talk, I'm going to actually MFT windows. Quantum field is based on energy coming from 33% power draw. So it's a third, 33 and a third. Power draw. Okay, corrosive element, corrosive element, corrosive element. Gas element, dissolving gas. So yeah, we can gas elements. I think we can use absorbent gas, dissolvent gas, absorbent gas. So basically, absorbent gas, chemical reactive gas. Okay, I don't think we should use reactive gas. So what? There's got to be another type of gas that we can think of. Yeah, reactive gas. Gas types. So we can, like, reactive gas can be like a chemical gas and absorbing. All right, so inert gas. All right, we'll use inert gas as a sort of like an idea. So the shield face, I actually want to have these all match. So can we do a boundary? And then can we balance these out? Align floating topics. Oh, yeah, I can't. Hey, check it out, bro. Okay, so the obviously we do different types of shields. So emission effect. So, all right. So the emission effect. The relationship with doodle-doo. I'm going to change that to a flashy. All right, maybe we'll just. Okay, I stasis effect, yeah, gas element, shield phase. Okay. Still a minute. Oh, let's do this one though. Right, okay, so I'm trying to work out how emitters work. All right, give me a minute. Dude. Hey. See, the process is basically sound anyway. Funnel light ribbons. Array. Projector array. A neutralizing agent. Okay, so we use the term neutralizing agent stasis element. again. We can use quantum field for this, inert gas for this, and shield face. Yeah. How many faces a shield has is purely down to sort of like the shape. So it's the angle at which you could split. So if we turn like okay, so if we wanted to create a sort of like okay, so let me just say important. If we wanted to create all right, so uh, okay. The emitter is made up of projector arrays and the neutralization injector. I think so. Let's see what a shield emitter looks like anyway. See, I'm just googling to see what other they created shields. So an emitter field. Okay, so thermal light ribbon project. Uh, okay. Uh, so shield facing ring lens. An example. I want to draw two examples. So let me just draw two examples. And then I can use maybe an extrapolation sort of like a thing. So draw. We use paint to do this. Okay, so in terms of what I want is this is a shield face, and this is a ring shield face. let's use white. Okay, so I don't want, again, let's see if I can just remove all this. Which again, with the shape of it. It's pretty cool, huh? Okay, so the difference between each of them though is okay. Uh, face 1 and 2. So okay, so uh, okay, so the core. A B C E F G H J, etc. And then I've got to add a core, so it's the blue. So again, all right. I think we can do that. So different sort of like face types. We do this, and then this. And then we can actually tie those two together to create a sort of like a face. We can use white to or erase it. So again, we'll just erase that. and the shield core would still be sort of like in the center, right? So again, if we have a raised one with multiple cores, different type. Okay. This is the thing, making DOM illustrations is kind of irritating, but you gotta do it. And then we'll just use black. No. I'm gonna erase this, and then we'll just. No, dude. There we go. Oh no, I'm just basic array and then an extended array. Okay. And then we'll just do the additional fields, which would be these ones here. And we'll put the injectors in. I think if we just put the injectors sort of like in sort of like a trivector area. Yeah. Okay, so shield cores, and then I'll put the injection methods there as well. Okay. Uh, do you know, like this is the thing. Once I've actually got something shaped wise. Okay. So I'm gonna show you what I've got now. So I'm gonna just give you sort of like an idea of what an emitter looks like uh, in terms of its shape and field. But they're very basic. So link URL douche. Copy image address. Tick. Okay. So again, can we actually include an illustration there? Can we just paste this as an illustration? Yeah. All right. So what we have is we have the emitter. I know it's probably too small. Let me see if I can paste it here. Oh. But yeah, no, we can't. We can paste it here. Can we increase the size of it? Yeah. Okay. So let me kind of try to explain what I'm talking about here with regards to how an emitter works in a way that it might make sense, might not. So in between, right, this is a basic shield face, right? So we have an A and a B and a shield core. So this is a two-phase shield array. So if you have two shield, again, this is where you've got the injectors. So you've got 2 points here. So think about how the shield looks. Yeah, it's kind of like let me just see shield emitters. How does a shield look in Star Citizen, right? In terms of like its actual, the actual product itself. So if we kind of like paste this is actually a shield. Okay. So the shield here is you're gonna have connections here. So you see these. Okay. What are these? We need to find out what these are gonna be. In terms of sort of like understanding what goes inside, what all these components and readouts do. So what do these lights do? What measurements and matrix it has. If you open it up, and then maybe we can have like different cylinders in there for gas, so you can replace that on the fly. And the type of gas that you use depends on, like, basically depends on where you are. You'd have to mine it if it's a specific one, if it's manufactured, if it's like a specialized gas that someone's made, a crafted gas. Then yeah, you get those sort of things. Now, what I predict could happen is if we do go down the elemental path and we create physical entities for every type of gas, solid, liquid, and then allow a sort of like a chemistry sort of like reaction sort of field. Again, you use all those sort of processes that we marked out here. So in terms of quantum effects, energy reaction, chemical reactions, and stuff like that, I might actually look into sort of like see if we can get an idea of how many of those we can get. But again, we need to have like an elemental effect. So basically, combine, if you add one element to another element, and then you have there, hello. If you have two elements, right, and you wanted to combine them using pressure or heat, so in terms of your thermal reaction, see, this is the thing about like once you have the sort of physics system in place in a video game, if you can simulate physics down on sort of like the entity level, then you can actually create weird effects for like ammunition and stuff. You can explain me a theory. What do you want to talk about anyway? So sorry, as pertain to, I don't know how long you've been watching or not. But again, Okay. Radiation. I have to think about like the way that elements work in sort of like the way that transmutation works as well. So it's like radiation pressure and energy expellation is when, say, two bonds are broken, etc. But I want to find out a way that we can have like a dynamic RNG method of producing effects that can be small in terms of its scale. So the difference between like combining two elements and getting a reaction, you'll have common reactions, then uncommon reactions, then rare reactions, and then like unique actions, which means that when you get a unique action, is that the gas is basically the purest form it can be, or the solid. Basically, your atom, your element, is the purest it can be at sort of like within its group. So that's something I need to work on. Deposition, vapor, the remotion, sublimation is the So yeah, I don't know if we've got a picture of shield emitters. Oh, okay, well this looks very similar to what I have actually thought of. Okay, so this is actually a sort of like an official one, like in terms of what it looks like. So that's kind of crazy. But yeah, it's very similar to what I'm doing, but it doesn't have the injector because it's not. Unless the internal. So this could be the case. It's like you can actually say this. So you've got the lens array for the outer and inner shield face wall. So the inner face is here. So what will happen is the gas will be produced within the inner face, and then the outer face is the outer bubble. And what happens is when two bubbles obviously connect, is that the membranes will actually just mesh together and create kind of like a wibbly wobbly bubble of energy. So it kind of like it makes just your standard soap bubble. And because of the soap, the effect of a soap bubble is that's you essentially can make it with as many faces as you want, right? But the shape has to be reformed, so the quantum field is actually stabilized. So you'll have another ring. I think if we have like the quantum field lens, because again, I want to have it so that the field is working. So yeah, but here's the thing about Einstein's theory. I know that Einstein is popularized as sort of like the physicist and the atoms, and obviously with people. But again, it is a lot. There are a lot of physicists that were involved in like the atom bomb, etc. I really need to do my research to kind of like find out the names of each of them. Well, there's like about 30 of them. And there'll be 30 more scientists, physicists. There'll be actually about 30 quantum physicists that are working on problems of solving complex math and, other things. But I don't want to go into details about like, there is a reason why I'm talking about this particular topic and pertaining to the video game that I play. Again, I don't like saying video game as well because it's not really a video game. Because again, it's a lot more than a video game. It's actually a simulated world, like a real one. And the fidelity is just basically based on technology and limitations of how long it takes. So basically, your time frame, how long it takes to create technology to create the actual product. So, but for virtual products like again force fields using exotic methods, I don't know, man. So let me have a look at this. Einstein's idea about planets circle flat. And I'm personally, I know I personally have a theory about the whole thing of the world being round and not. Because if you think about it, if you look into the space, everything shrinks down to the shape of your light cones, which is circular. If they're spherical in shape, everything, will be circular. So that's why the world is a sphere. Because if we go up high enough, we start taking in the light. We can't take out, we it depends on the surface area. I don't know how high we've actually ever been physically, but turns out like people going to space in Origin rockets, they just see the horizon still when they get to space. It's just they become light because they're falling. Technically, Jeff Bezos has made a really expensive way of getting people into low Earth orbit. No, they haven't. He's not even in orbit. This is the thing about like Jeff Bezos and Richard Branson. They can't do space. They're shit. They've been scamming money from the state for a long time with defense contracts. So I did say I don't know. Like as I said, you're giving me a theory, but I'm not 100% sure if it's a question or a theory. So you got like I'm self-taught with a lot of my stuff, so I'm trying to still learn like what algebra and all that shit is because I can go off about quantum physics and shit for a while, but I don't know jack shit about it. Not, but then if I start looking into it, I'll probably know more than I'm supposed to, because that's just how things happen, isn't it? It's like how do you know so much? I don't know. Never mind. Okay. Yeah, but this is the thing: is like the Earth is actually a reflection of the shape of the internal sphere of the body. It's like as above, so below. Because I'm a hermetic teacher as well, so again, like I can explain these things. Science and hermeticism, there's like very little intersection between the two. Is that there basically is hermeticism is the simple format, and then the more complex format is taking alchemy and then just changing the description of it. It just makes it overly complicated when it's not overly complicated. You can break everything down into basic elements, right? Because we got a periodic table of all these elements, so the base elements. This is the reason why we need a sort of like in star system, we do need a basic element table for gases and solids, and then to actually build like a library of different materials like fibers. So like how does a fiber behave? A fiber is basically if it is torched by any point, is that it actually burns horizontally to its mass, or sorry, vertically or horizontally. So if say something is coming upwards, yeah, so it's growing from its base root, and I can't. There's no way. Is there a whiteboard on this? Because that would be awesome. Actually, there's a whiteboard on my thing, so let me just move this over here. So we do the whiteboard. Does that work? Is it locked? No, it's unlocked. Okay, so let's lock it in place again. Nope, it's not letting me. Okay, never mind. So I mean, we can use a fiber as a sort of like an example. So what is a fiber? A fiber is technically, it's usually in terms of an element that is being compressed and stacked. So a fiber is just basically a vertical stack of elements. So in terms of how do we connect these fibers? So let's change this to right facing. Doo-doo-doo. And then this is downward facing or upward facing. Sure. Okay, let's use this one. So element. So it's like blocks of fiber. So in terms of sort of like a fiber would be element bond, element bond, element bond, element bond, right? Right. No, 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 I want blue. Oh, come on, dude. It's black. Okay, so element bond, and we're going to use red, element, red, element. And then we'll use blue for bond. Did I use, what was it, purple or blue was it? Okay, so bonds are element and red is element. Okay, so the way that I have it is if a fiber is basically it's a continuous version of an element, depending on the micro scale. So the basically it's a stack up, it's a vertical stack, fiber vertical stack. So it's energy or pressure. Pressure. Okay, so bonds are broken. Use tension. So pressure can be used. Okay, so the tension. Tension of a bond based on the um so these are basically, this is a fiber example of a fiber. Of fiber bonds. Okay. Fiber is a 1D element. Not plane. So material. Okay, so materials are packed when we a material. Okay, so let me see this. So what I have is a example of linear bond, fiber bond. So this is element bond, element bond, element bond. So this is vertical. So I should actually change this to a vertical. So like maybe um that's not good. That's also no good unless we do all of them the same. Wait a minute. Okay, there you go. That looks a little bit better. An example of a linear bond. So element, bond, element, bond, element. Okay, and you extrude this. These type of materials are extruded. Fibers are what it is. Okay, so again, the free material. So material. Okay. That's a silly one here. It's 2 hours of this stuff, man. Like this is the thing. When I get into something like this, it's like my brain just won't shut up until I've fixed it. Like I've actually done a lot of it. So this is a fiber bond example of okay. So these are type of experiments you can do. Can we do a boundary around it? No? Okay. Never mind. So composite elements. So this is an example of how you would do it. So it would decay this, but if... Okay. So... corrosive decay properties. So if we're talking about, okay, we're talking about okay, so okay, so the gas element and the chemical bond. So there's a gas in this. So no, released. Okay, so if you use a corrosive element on, say, a material like like an acid, right? So what's going to happen is that the material element is going to be decayed. You're going to lose the yield of it. So let's... element decay as percentage element remains. So decay that remains. The corrosion value reset. So Okay, so corrosive elements can affect material elements to the resistance. This is the K value. Okay, so so okay, what is it called? Transmutation, dude. Come on. Oh my god, there's 22 states of matter, and I'm only working on 5. Because we go on to a BEC, etc. Really? Come on. So I know plasma and beyond plasma is Bose-Einstein condensate, right? It's basically what happens when you heat a plasma beyond its transmutation state. It will turn back into its own. It will turn into an inversion of gas. So like, it's the condensate plasma. But again, it requires a lot of energy to get to that state. So, but ionization is energy, so it's basically electricity. Okay, be right back. do. All right. Oh. This is like the most annoying part right now. So again, in terms of that released as energy, so gas, element A, bond, gas, released. Bonds removed, element is decay. Let me, I've got to check and see if this is correct. It's oxidization. To form hydrated iron. So yeah, okay, so oxidize. It's a natural process where iron metal comes into contact with oxygen and water. Okay, so okay, so an iron isotope has 2.6 million years. So this is why like if we use quantum fields in terms of crafting and we actually create a sort of process to accelerate and decelerate time, like use the entropic effect of quantum fields, we can do so much with that because we can actually take, say, for instance, something that has a chemical process that takes the transmutation of, say, iron. Yeah, so an iron isotope has a half-life of 2.6 million years. So if we can create a dense quantum field that accelerates time inside that field, we and that way we can actually we can measure sort of like how fast it takes. All right. So this is the reason why I'm so interested in the science stuff being in game, and it's not because I could talk about this stuff like for a long time, but it's a case of whether or not like CIG is actually paying attention to what I'm talking about. which, you know, egocentrism, you know, the big corporation company doesn't need to listen to little people, but they do. It's just they need to not listen to little people that are stupid. Okay, so again, natural processing, for instance, is rusting, aka Rust. This is, I mean, this is good because again, if you use quantum fields for like life forms as well, is that you can create what we call as a pocket of sped up time or slowed down time. So I it's quite annoying that I can't think of much else at this point. I don't want to get fatigued because like when you feel like you're actually onto something and then it's like, yeah, no. Okay, so let me just put a boundary around that shit as well and then move it. How do we, all right, delete. Can I put a boundary around you guys? All right. Fiber element is so again, just wanna, I want to group these together so I can sort of work things out. What if we do that and then we can attach this to this? There you go, we're done. And that way we can just do this and boundary it and then just say example of element. Corrosive properties. Plasma state as. Okay, so if I so the okay, so corrosive properties, so corrosive enzyme. This one here. Element C. Element A is a gas. So mineral element and a gas element. So let's say if we make, we can create a plant. All right, so we'll use fibers to create plants. In terms of how a plant will grow, all right, it would be a case of how many, like what the array of the fiber is going to be. So you'll have like the shape of a fiber would be something sort of like along the lines of an element, and another element. So let me see if I can kind of like do a sort of like a chart here. So let's say we have a simple trivector sort of like element, right? So what will actually be there is that you'll also have your bonds. So periodic element. So an element is just basically specific. So bond, bond, bond. And then okay, so again we get I don't know, you know. Like the thing is like I actually want to have that connected to this. So in terms of sort of like a shape, how do we do this in a way that it's going to look good? So let me. I can use 3D Paint instead, I think. Let's make a new one. Don't save. Okay, so 3D shape. So what we're going to do, we go with a sphere. Okay. Another sphere. And another sphere. And then between those, we're going to do it's a shame we can't do like a way to just like snap them together. Yeah, it's crashed. Okay, so we can use MolView. Okay. Um, So, okay, so steel is basically it's an iron atom with a carbon atom. So what we're doing is we're gonna have, okay, so that makes more sense. So what we have is that is an element, and then what is the carbon atom used for? Increases its strength. Is it a bonding? Okay, so let's have a look at this. So this is what we call as an iron molecule. So this is ion. And then the steel molecular structure is actually just basically this. Okay. So it's a tetrahedron, three-sided pyramid, four faces, including a base. So carbon is basically what we use is. All right, so that makes sense. I kind of see where what we're doing. So carbon molecular structure. Because if I can actually make it so it's visually representational, that's methane, that's carbon. I want to see what carbon looks like clear level. Because there's also graphene, and the way that graphene works is 2D, 3D graphene. You got different types, basically. The thing about graphene is that it works as like a framework. Let me give you an example of graphene. So we'll basically graphene here. No, not that. Copy image. Delete that. Whoosh. No, again. Okay. Reject. Copy image. Space. There you go. So the thing about this is graphene is actually a carbon atom. So again, all carbon atoms are like hexagonal in shape, right? So if you can put this particular atom array in it, so what is the molecular for steel? Which again is like this. Okay, does this make sense to you all? So again, this is essentially what a carbon atom is. Let's change the thing to the right. Okay, so we have those two together, and then the conjunction. If you have, I think it's an array. So if you set, you could create an array, right? So if we create the carbon side of it, all right, which is here. So these different types of carbon, graphene, etc. That should actually be larger. So like that size. Okay. So this is in the sort of like the one, sort of like D. I don't know what the bond is. So again, there's in the process of creating these and these, you need a fusion element. So if you use I think manganese is it, and silicone. So these are bonding agents. And so let me have a look at that. Like magnet. Okay, so what? I got to work out what is it. So what is the purpose of manganese? Manganese removes oxygen and sulfur when. Okay. So all right. So manganese is all right. Because if I can actually sort of like work this out, it would make it look a lot cooler. Types of carbon. Okay, types of carbon means. Or maybe I'm getting this wrong. I don't want. Let's say this is stupid. So if we put this inside this, then we get this. So, but these are quite big. So, and these are quite small. So maybe it's the distance between the carbon atoms. Okay. I think I'm getting smarter just by doing this. stupid. Um, but again, if there is a way to design a sort of method of simulating chemical bonds and stuff, and then creating materials with properties, specifically, it's just a case of the materials that you'd use is a solid material with a texture. So it's a case of it's a square block of opaque or translucent, depending on what it is. If it's a crystal, it's translucent. So like ice, gemstone, etc., translucent. If it's an opaque solid, so like a mineral, proper mineral, then you can't see through it. So there's no crystalline carbon structure to it. I've actually got to look that up. So what is salt crystal, ice crystal? So we're looking at how far apart uh so in quartz it's silicone as oxygen and silicone as a base, and then things like salt crystals like chlorine and sodium, and for ice crystals it's oxygen and hydrogen, so it's just basically a solid state of matter. Again, extrusion. So the way that quartz and other crystals form is usually through like it enters the oxidization, so that the transmutation formula is basically hydrogen and oxygen, so moisture, and thus thus the crystallization of rust, etc., for the same reason. Okay, think that's essentially where I can go. So again, in terms of a structure, so this would be so the pressure so okay, so how am I going to do this? So again, See, I know this. The weird part about this is that it's the crazy properties that you can create, especially. So like all this oh God, you know what? I wonder how the developers of R simulation was going through a lot of the stuff, because again, this the thing about um creativity and invention is that if it's once it's thought of and then it's rationalized, then it's materialized, and then it's utilized. But then after that point, it's controlled and destroyed. So you got the generation, operation, and destruction of everything. God, bro. Whereas dogs do the opposite. What they do is they destroy, and then they operate, and then they generate by shitting and pissing on everything and creating plants. And that's part of the flora fauna system that I wanted to create. Which I'm going to open up another map in a minute to see that. So this one's kind of like a dodgy one. How does this actually pertain to work in there? I want to know how this is this sort of material works. So I don't know. This is a basic one for an emitter. Again, you got a webbed matrix here, so I don't know if that's an energy sort of like extrapolation thing. But if this is supposed to be like an arc reactor or something, it looks ugly as fuck. Okay. Relationship to this is molecular bond. Is it an electron? What can it like? What is the bond? So in enzymes cultivate the what is a, how do you pronounce this? Okay, let me see if I can read this in my head. Where is it? Where's the okay. Covalent. What? All right. Okay. So what is a covalent? Involving two atoms sharing one or more pairs of electrons that hold them together. All right. So an electron is a state of. So each element. So again. Okay, so an electron particle that have a negative charge equal to -1. So how do we map? How do we create a gameplay sort of like electron? Okay, so I've got to create another element here. Electron. Types of elements. I'm gonna. That's an electron. So we're going to change this border to this, and then we'll change it to like a pale blue, and then we'll remove no fill. We'll do no fill. So we'll do. That's a base element. Electron. Atomic, therefore, it has 5 protons and 5 electrons. So an electron is the bond, right? So if I'm doing this, the bond is an electron. Okay, so there are 3 primary types of bonding: covalent, ionic, and metallic. Okay, let me have a look at these atomic bondings so I can get an idea of what I'm talking about before I start applying it. So ionic bonds, we're talking what a negative and positive ion, right? Covalent is molecular bonding, and metallic bonding. Metallic is formed when. What does valence mean? Okay, let me have a look at this word, because now I'm actually starting to discover stuff that I didn't know. Okay, so in chemistry, valence or valency is of an atom is measured of combining. Let's see if I can find something that I can explain it with. So this is the really weird part, is that, you know, I can learn information on the fly, I can process it, I can understand it, I can dump it into words and stuff like that, but I can't revisit it and then explain what I exactly did. because I'm stupid. Okay. Bro, if I come out of this like just basically having enthusiasm about a game, okay, in terms of that. So, all right, so Valencia of the 30 elements. Yeah, we can use this. Can we? All right, we can't copy pasta it, but we can do a grid, I think. Yeah, no, maybe. Okay. Okay, so this is how we get our atomic table, I guess. So atomic stuff is quite important. Chromium, titanium, cadmium. So these are basic elements that we find on Earth, right? But if we do exotic elements, it's going to be like we need to know what properties we can extract from other elements and then just use specifically. I know this information just like wrote itself. It just came out of my anus. Okay, where are we? Where are we? So ooh, potassium is a lovely one. We like that. Cesium, fluorine. So fluorine, cobalt, nickel, oxygen. All right, that's an inert gas. Nitrogen, yeah, it's an inert gas. Carbon. That's one of our important. So carbon's the important one. So carbon and iron, that's steel. Manganese. You need that to create, and I think chloroform or chlorine. It's those elements specifically in phase. You're going to need percentages, and it tells you how much of each of those that you're going to need. So I've got 30 elements here we can use, but then we can create new elements by combining these base elements. What is a periodic table? Let me have a look. Which is a lot more than what we got here. So, all right, periodic table. Okay, so that's one. Let me have a look because I think it's these are specifically these are actual physical elements. So these would be liquids and solids and gases, which don't emit radiation or not. One, two, three, four, five, six, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. That's 16. All right. So it's carbon, oxygen, nitrogen. In terms of how they go on the table, and then fluorine. So we find out what properties each of these can have. We can actually apply them. So like if it's, again, once you get to sort of like your time scaling of each of these, depending on how like, you know, the density of the particle. So the higher the amount of particles in the container, the more viscous it becomes till it's, you know, the pressure equalizes and you can't go through it. So it depends on if a human can actually go through it as well, whether or not the pressure is going to kill you on passing through the gas. So whether or not the gas is actually going to be poisonous to you, so to speak, which is usually where it's permeable through what you're made out of. So if you're a carbon-based life form, then you don't want to have carbon and stuff coming through you. Okay, so how did I do this? So fluorine. Can we make these into little squares? Actually, no, make more squares. We'll turn them into circles. No, definitely not. Little pills. No. Heck, that works because we can actually make a periodic table using these things, which is good. So let's start with you. You can be the actual beginner. The table tree. Okay, so no. The matrix. The matrix hash. Okay, not that one. Oh, did we forget nitrogen? Nitrogen's actually before. So carbon, nitrogen, oxygen, fluorine. Okay. Carbon, nitrogen, oxygen, fluorine. Fuck, I can't even read that. It's so small. Oh wow. Also, I find this kind of interesting. Yeah. Okay, so chlorine is actually beneath you. No, that's the wrong one. And it's sulfur. Blech. And it's sulfur, you are beneath this dude here. And there you go. Fixed it. What is underneath this? Phosphorus. Okay. That's inert, that's phosphorus. What's underneath carbon? Silicon. Do we actually have silicon here though? Beryllium and lithium and helium and aluminum. I don't know these things, but I know what they do. Atomic number and Valancias. So okay, so yeah, there we go. Oh no, you don't want to do that. So selenium and bromine. I don't think selenium's on the list. Oh well. Man, I'm getting burnt out now. I've been at this for hours. 3 hours so far. Never mind. Alright, I'll call it a night.